Hey guys, welcome. Today we're going to solve Leetcode number 98, validate binary search tree. As before, I'm doing this problem live and I'm seeing this problem for the first time, so please be patient with me and enjoy. So the problem statement is as follows. Given a binary tree, determine if it is a valid binary search tree. Okay, and assume a BST or binary search tree is defined as follows. The left subtree of a node contains only nodes with keys less than the node's key. The right subtree of a node contains only nodes with keys greater than the node's key. Both left and right subtrees must also be binary search trees. So this is an example. Okay, so let's first break this problem down. So input, we are given some root node. Let's see. Yep, that's right. We're given a root node, and the definition of that tree node is defined here, where within this tree node class we have a value, we have left and right as internal fields. So tree node, so input we have tree node called root. Output, we're supposed to be returning some sort of a boolean, true if valid, false if not. Okay, so assumptions, right? A very big assumption here is that we're given a binary search tree, right? Of course, there are some edge cases. What do we return if root is null? If root none, then return false. I'm just going to assume that. Okay, and we are also assuming that the fields input values are integers, right? But the integers can be either negative or positive, so any integers essentially. Okay, so let's think about this. So what are some of let's think about approaches, right? What can we do? And then we should also think about bottlenecks as we come up with approaches and optimization at the end of it. So let's see, what can we do here? So let's say we're given this tree, right? So we have 2 at the root, we have 1, we have 3. Okay, so one way of checking if this is a valid binary search tree is what we could do. Let's see, one of a simpler and really straightforward approach is what we could do is we can generate a list of values from doing in order walk, and after that we can simply traverse left to right, check if values to the right are greater than current value, right? So it's a simple check. So what I'm proposing here is one of the approaches would be to do an in order walk, and what we'll get, for example, for this tree we'll get something like 1 2 3, and because this is a binary search tree, right, is within our assumption here, the order of the values within this list should be in ascending order. So let's do a quick complexity analysis. So in terms of time, it'll take O of n time and O of n space, right? To be precise, 2 of n, because we are traversing the tree n nodes and we are traversing n elements within the list, so that's 2n. So now let's think about, what about O of 1 approach, right? O of 1 space approach. Is there a way for us to do this in place? Another thing that something that I'm thinking about is what we could do is we can still do in order walk, but let's see, we can do a recursive call, in order walk recursive call, but instead of having to input the values into a list, we can just do a check right within the recursive call. And what we can possibly do here is we can pass in some minimum and maximum, and really all we have to do so what I'm saying is that within each recursive call we can pass in some sort of a minimum value and a maximum value set by something from the top of the recursive call. And all we have to do is within each recursion we only have to check this whether a node is within that range or not. So recursion with min and max parameters, right? So this is what I mean. So let's say we're starting at the root. Min is, so when we are starting initially, we'll set min to the extreme minimum and max to the extreme maximum, right? Once we hit the first node, which is 2, and it really depends on, okay, once we hit the root node, right, we know that 2 is within min and max, so we know that 2 is valid. So now here's the sort of tricky part. So when from 2, when we go to the left subtree, we have to update the maximum value to 2. So now when we hit the recursive call of the left subtree of the child node, which is 1 here, right, we know that 1 is greater than current minimum and 1 is also less than 2, which is the new maximum. So if we were to do it this way, it'll take O of 1 space and so let's write this down here with min and max parameters. So O of 1 space, and as usual, because we are doing in order walk, the runtime will still be O of n. Okay, so I think from now it's going to be pretty straightforward in terms of implementation. So let's think about, oh, and another thing about this approach is that each recursion will return boolean, right? If for whatever reason current value of that recursive call is not within the range that was passed in from the previous recursive call, it'll return false, right? Okay, return false if current node not within range. I hope that's clear. So let me try to implement this in code, and that might help you to better understand what I mean. So what I'm thinking of doing here is, let's say we're implementing, because we're given a class here, I'm going to implement an internal, let's see, can I set this to Python 3? Uh-oh, just lost all my notes. Let's try that again. Yeah, I just prefer Python 3. Okay, let's paste that note in here. Okay, so because this is a class, what I usually like to do is I like to implement helper functions as a private function, and in Python you do double underscores to denote that a method is private. And in this case, we're going to implement a helper called in order walk, right? And and as I was saying earlier, we are going for each recursion call. We are going to check whether root is within some min and max range, right? If not, we'll return false. If true, we keep calling on the child nodes, which is the left and the right of that root node. The left child node and the right child node of the root node. Okay, so this is what I mean essentially. So, and as always, don't forget self. Okay, so so another thing we have to also think about is what do we return if root is none, right? So if root is none, then we return true. So it's still okay. Okay, so now if root is within max, right, and root dot val is greater than min, let's see, can we assume that there are no duplicates? We can. Yeah, typically. Okay, so let's assume that all nodes are unique for now. Okay. All right. So if that is true, then we'll recursively check the left subtree. We'll do the same for the left subtree. So now in the next recursive call, root becomes the left child node of the current root. So now because we are traversing to the left subtree, we have to update the maximum to be the current value, which is root.val, and we'll leave minimum the same, right? And the reason for that, if you think about, if we have to go back to the definition of a binary search tree, root or whatever the root is, if that node is a left subtree, is the left node of the root, then that node by definition of binary search tree has to be less than the parent node. Okay, yeah, that's the word I'm looking for. I've been stumbling over that. So if one is the left child of 2, by definition of binary search tree, left child has to be less than parent. Okay, that is why I'm updating maximum to root.val here when I'm recursively calling on the left subtree. And we'll do the same, but instead of updating max, we'll update min to be root.val, and we'll leave max the same. And finally we'll return n of the 2, right? In order for this subtree to be valid, both of its left and right subtree has to be valid. This is why I'm doing and here. Else, simply return false here. And I believe this is it. This is all we have to do. And so let's set max to be, so let's import sys. In Python we can get the maximum value by calling max size. Actually, let me check max size Python. Okay, that's the right. I think that's the right way of the calling. Okay, and minimum will be max size times -1. Okay, let's see if that works. Okay, I think this code is good to go, so let's give it a go. Nice. So let's see, how did we do? So we beat it 85% of the people. Okay, thank you for watching and see you next time.